Everything looks ready. The rocket is stacked. The infrastructure is humming. The world is watching. And yet, Starship Flight 9 still hasn't been cleared for launch. Why? While SpaceX continues to move at breakneck speed, testing, tweaking, upgrading, the FAA remains silent. No green light, no final permit. Just a growing pause that's hard to ignore. Is it just bureaucracy at work? Or is there something deeper, more technical that's holding things back? In this video, we dive into the tension between rapid innovation and regulatory caution. We'll look at why SpaceX might not be catching the booster this time and why that matters. We'll unpack ongoing concerns about altimeter glitches, those pesky height measurement errors that still haven't been fully solved. And we'll explore strange shifts in hardware behavior, from sudden destacking events to mysterious new chopstick tests on Pad B. Not to mention Starship Gen III, an unexpected wildcard thrown into the mix. When you connect the dots, a bigger picture begins to emerge. Something is stalling Flight 9, and it's not just red tape. So, what's really going on behind those closed FAA doors? Let's find out. FAA delays approval for Flight 9 despite SpaceX's progress. On May 12th, Ship 29 was restacked onto Booster 11 at the orbital launch mount, fully integrated, tower arms released, and all systems seemingly aligned for a dress rehearsal. It was a clear signal. SpaceX was gearing up. Then on May 14th, the company submitted a formal request to the FAA, seeking a license modification for Flight 9. That was days ago, and yet no response. As of today, the FAA has not granted clearance. No date, no launch window, just silence. The timing feels off. In previous launches, FAA approvals often landed within days of final stacking. But now, even as SpaceX accelerates preparations, regulators remain unmoved. It's creating a pressure gap, a growing tension between what's happening on the ground and what's not happening on paper. This isn't just paperwork lag. There's a pattern. Flight 9 was originally expected to launch in late April or early May. But by mid-May, multiple signs pointed to a delay. SpaceX proceeded anyway, closing cryogenic tests, restacking hardware, even performing pad drills. But these are steps you take when you're expecting a launch, not when you're still unsure if the FAA will say yes. Aviation sources close to the matter suggest that internal reviews are ongoing, possibly tied to data from Flight 8 or technical changes in Flight 9's mission profile. That includes structural tweaks, trajectory adjustments, and most notably, the strong possibility that Booster 11 will not be caught by the tower arms during descent. Now let's pause for a second. Imagine being SpaceX. You've modified your vehicle. You've tested everything you can. You've signaled readiness, regulatory approval. Everything stops. Time slips. Momentum stalls. And the public starts to ask, what's the holdup? To be fair, the FAA isn't just a rubber stamp. Their job is to assess flight risk, not just for the rocket, but for people, airspace, and infrastructure. So, when the FAA hesitates, it may mean they see something the rest of us don't. Or, they're still working through an unusually complex web of updates. Either way, it's not business as usual. Flight 9's timeline has already stretched far beyond initial estimates. And with each passing day, expectations grow. So does speculation. Is it about safety protocols not being met? Incomplete data from past flights? Unresolved hardware issues? We can't know for sure, but the delay itself has become a signal. Something isn't sitting right. What was supposed to be a seamless step forward is now suspended in uncertainty. And as we wait for clearance, one big question looms larger than the rest. Why isn't SpaceX planning to catch the booster this time? Let's take a closer look. Technical risks of not catching the booster in Flight 9. Why would SpaceX decide not to catch the booster this time? That question has sparked intense debate across aerospace forums and launch commentary circles. On the surface, the decision seems like a step backward, especially after Flight 8's semi-successful attempt. But dig deeper, and the logic begins to reveal itself. Let's rewind to March 14th, 2024, Flight 3. That mission ended with Booster 10 crashing into the Gulf due to loss of control during descent. No catching attempt was made. Then came Flight 4, where SpaceX for the first time attempted a soft landing directly onto the launch mount, using the chopsticks not only as guide rails, but as a hypothetical catch mechanism. The result? The booster got close, but telemetry showed significant oscillations near the final approach. It missed. No physical damage, but clear indications that precision alignment was not yet reliable. By Flight 6, SpaceX had fine-tuned descent control, but still no real catching occurred. And while Flight 8 came close, with the tower arms waiting and the booster descending cleanly, last-minute yaw deviations once again forced an abort on the catch attempt. And what do we know? Multiple sources, including leaked internal memos from early May, suggest that Booster 11 will not attempt a tower catch. And what do we know? Multiple sources, including leaked internal memos from early May, suggest that Booster 11 will not attempt a tower catch. Instead, it will aim for a controlled ocean splashdown, similar to Falcon 9's early landings. Why the change? The answer likely lies in risk management. A failed catch attempt isn't just a lost booster. It could mean serious damage to the launch tower, which would take weeks or even months to repair. Starbase has only one operational launch pad. A crash into the chopsticks wouldn't just delay one flight, it could halt the entire Starship program. From a regulatory standpoint, this is also a red flag. The FAA may be hesitant to approve a high-risk maneuver that hasn't yet succeeded in practice. Each failed catch increases scrutiny. The physics doesn't help either. Starship boosters are massive, over 70 meters tall, with more than 30 Raptor engines. Trying to guide that kind of mass into the mechanical grip of two steel arms, with crosswinds and minor guidance delays, is like threading a needle during an earthquake. According to SpaceX's own simulations, even a 2-degree tilt in final approach can lead to a lateral offset of several meters, enough to strike the tower. And we're not talking about a soft bump. We're talking about tens of thousands of tons moving at terminal velocity. Given that, the safer play is clear. Don't risk the tower. Instead, splash down. Recover what you can. Analyze performance data. Live to fly again. Of course, this isn't an admission of failure. It's strategic patience. SpaceX has always embraced rapid iteration, but even that has limits. When the risk of catastrophic infrastructure damage outweighs the benefit of demonstration, the calculus changes. There's also a subtler strategy at play. By delaying the catch until Gen 3 hardware is fully implemented, SpaceX may be buying time, refining algorithms, hardening the chopsticks, adjusting mass profiles, until the odds are better. So, in the grand scheme, skipping the catch might not be a retreat, but a reset. Still, the booster isn't the only concern. Another problem has quietly persisted and could be just as critical. Let's talk about altitude errors. Altitude measurement issues and unresolved errors. one of the most persistent and under-discussed technical hurdles in Starship development has been altitude measurement. Specifically, a recurring issue with the booster's radar altimeter system. During Flight 8, telemetry logs revealed a sudden and unexplained altitude drift in the final 20 seconds of descent. The system reported a false positive, indicating the booster was higher than it actually was. This discrepancy forced last-minute corrections and may have contributed to the aborted catch maneuver. Engineers later confirmed the root cause: signal interference between the altimeter's downward radar and the plasma sheath generated during re-entry. Essentially, the system was seeing static and mistaking it for altitude data. It's not a new problem in rocketry, but in Starship's case, the scale and speed of the vehicle exacerbate the issue. When descending at several hundred kilometers per hour, even a few meters of miscalculation can mean the difference between a clean alignment and a catastrophic impact. Post-Flight 8 diagnostics showed an average vertical deviation of 3.7 meters in the last descent phase, well beyond the margin of error for a tower catch attempt. To address this, SpaceX began integrating a hybrid sensor suite combining radar altimetry with LiDAR overlays and inertial guidance input. The idea: to cross-reference multiple data streams and build a more stable descent profile. Initial ground tests using this hybrid approach began in late April. The new system was mounted on a modified prototype and dropped from altitude using a high-altitude balloon to simulate the final 20 seconds of descent. Results were mixed. In 7 of 10 trials, the system successfully corrected for false positives by weighing LiDAR data more heavily. But in 3 cases, guidance still overcompensated, introducing lateral instability that could prove dangerous in a real flight. Software updates were pushed in early May, tuning the weighting algorithm to favor predictive momentum modeling over reactive correction. Engineers remain cautiously optimistic, but the fix is not bulletproof. And here's the catch: the FAA knows this. When you're proposing to land a 3,000-ton booster within inches of steel tower arms, sensor confidence has to be near absolute. Even a 1-meter deviation at that speed can be catastrophic. That's why, despite SpaceX's rapid iteration, the system is still flagged internally as under watch, a classification meaning it's functional but not fully validated for high-risk maneuvers. The altimeter glitch isn't grounding Flight 9 by itself, but it's one of several compounding factors adding friction to FAA approval. It introduces a layer of uncertainty at the most critical moment of flight: final descent. So is the fix stable? Can we trust the new system? The short answer: it's promising, but not proven. Not yet. What we do know is that SpaceX is treating this issue seriously. The hybrid altimetry stack is being tested, refined, and monitored in simulation and live trials. Engineering reports show continual improvements in signal clarity and cross-check reliability. And for now, the company seems content to operate within those limits, opting for splashdown recovery while these final technical edges are smoothed out. But that's not the only variable in play. In the past few weeks, SpaceX has made several strange moves: hardware reconfigurations, unannounced destackings, and activity at Pad B involving the launch tower arms. What exactly is going on with these technical shifts? Let's take a closer look. Recent technical changes: destack operations and chopstick Pad B testing. In early May, something unexpected happened at Starbase. Just days after Ship 29 was fully stacked onto Booster 11, the two were suddenly destacked, lowered, separated, and moved back into staging. No public explanation, no official comment, but clearly something had shifted. At ground level, teams moved quickly. Tower arms were retracted. The booster was rolled back for inspection, while Ship 29 was temporarily secured at the launch mount, still connected to ground umbilicals, but no longer flight-ready. Observers noted new scaffolding installed at the upper catch arms, specifically on Pad B's chopstick mechanism. By May 9th, engineers were seen testing hydraulic articulation on the arm joints, simulating slow-motion grit sequences at various altitudes. This wasn't routine maintenance. It looked like calibration. Why? Likely to fine-tune force distribution, timing sequences, or structural alignment, especially after recent feedback from failed catch simulations during Flight 8. Following the chopstick trials, the team began reinforcing the launch ring clamps, those massive mechanical hooks that secure the booster during pre-launch and post-landing phases. Crews added thermal shielding and adjusted actuator timing modules, indicating a concern about stress loads during high-thrust ignition or deceleration events. Next came adjustments to the quick disconnect umbilicals on the ship side. These are the lines that feed power, data, and fuel into Starship before launch and disconnect milliseconds before liftoff. Engineers swapped out sensor arrays, suggesting improved diagnostics or faster fault detection was being implemented. From there, attention turned to ground staging areas. New vibration dampers were installed on the transport mounts, and the booster transfer rails were realigned. A subtle but telling move. It implies SpaceX is trying to reduce micro-misalignment between transport, staging, and lift operations. When you look at all of this together, a picture starts to form. SpaceX isn't just tuning the launch system, they're preparing for variability. These upgrades suggest a system being hardened, not only for routine launches, but for contingencies, partial catches, aborted sequences, fallback landings. As one engineer, who spoke under anonymity, put it, the margin for error on these systems is razor thin. A centimeter of lateral drift at 70 meters up becomes half a meter by the time you land. We're adjusting for that, mechanically and in code. It's a reminder of how interconnected every element of the Starship system really is. The chopsticks aren't just arms, they're dynamic actuators. The clamps aren't just locks, they're stress absorbers. Every wire, every bolt, every pivot point has to sync like a nervous system, not just a skeleton. But perhaps most interesting is this. All of these adjustments are being made while a new generation of hardware looms in the background. Because quietly, Gen 3 starships are coming online. Bigger, heavier, stronger. And their arrival may just change everything. Starship Gen 3 upgrades introduce new variables. Something new has appeared at Starbase. Towering in the background of recent operations is a starship with subtle but unmistakable differences. Reinforced aft flaps, thicker thermal shielding, and a modified interstage with what looks like embedded hardpoints, possibly for structural load balancing or sensor arrays. Observers first noticed this variant in mid-April, tucked away in the high bay. It didn't match Ship 29 or any of the prior models. The body was broader near the midsection. The weld seams were tighter, and the nose cone appeared slightly more compact, perhaps to optimize mass distribution. This is no minor tweak. We're looking at the early form of Starship Gen 3. Technicians have been spotted, applying additional insulation panels along the ship's belly, possibly for enhanced thermal protection during more aggressive re-entry trajectories. At the same time, new actuator assemblies were fitted to the flaps, hinting at stronger vector control or finer maneuverability during descent. None of this has been officially confirmed by SpaceX, But based on the visible modifications, it's clear that Gen 3 isn't just about iteration. It's about a shift in mission architecture. Some analysts speculate that these changes are meant to support deep space missions, including lunar cargo or crewed Artemis variants. Others suggest it's an early move toward partial reusability in more hostile atmospheric conditions, such as Mars entry. Could this new variant be carrying more propellant, improved life support payload space, stronger structural endurance to support a second stage catch attempt in the future? We don't know yet, but the speculation is growing. What we do know is this: with every new hardware generation, SpaceX redefines the operating boundaries of Starship. Gen 3 could offer better heat shielding, smoother engine restarts, and tighter integration with both Falcon legacy systems and next-gen ground operations. From a strategic standpoint, these upgrades matter. They allow for increased mission flexibility, more Delta-V for longer burns, higher reliability for satellite mega constellations. And critically, they future-proof the system for missions where no recovery is possible, where everything has to work on the first try. Even from a regulatory angle, Gen 3 adds complexity. A new generation means new simulations, fresh certifications, and in some cases, entirely new risk models. That could be contributing to the FAA's hesitance around Flight 9. After all, if the upcoming vehicles look drastically different from the current test articles, the review process must evolve with them. But take a step back, and the bigger picture is breathtaking. SpaceX is no longer just launching rockets. They're sculpting a launch system capable of adapting across time, across missions, across planets. Gen 3 isn't just a new version, it's a new philosophy. It tells us that SpaceX isn't slowing down. If anything, they're designing for a future that regulators haven't fully caught up with yet. And that's what makes this moment so powerful. Because under all the scaffolding, behind all the testing, what we're really witnessing is the scaffolding of a new era in spaceflight. So where does that leave us now? Let's bring it all together. As of this moment, one of the chopstick arms at Pad B still holds its test angle, frozen mid-position, as if waiting for a decision not yet made. A quiet detail, easily missed, but it says everything. The system isn't shut down, it's simply paused. Across Starbase, the signs of momentum are everywhere. Technicians are still moving, cables are still being routed, Booster 11 is still on standby. And yet, nothing flies until the FAA says go. We're now in a complex chapter where technical readiness, regulatory caution, and long-term planning all intersect. On the one hand, SpaceX is sprinting, refining booster control, deploying new sensor suites, and rolling out Gen 3 hardware faster than ever. On the other hand, FAA procedures are evolving too, especially with public scrutiny increasing, and national discussions around launch risk and aerospace policy gaining weight. Add in NASA's shifting timelines and federal budget negotiations, and you've got a perfect storm of ambition and delay. The impact? It's not just about one flight, it's about momentum. A missed window today ripples into the next quarter. A denied permit could slow the entire Starship cadence. Every pause has a price. So what exactly are we looking at here? Is it just a temporary snag, or the growing pains of a system that's expanding faster than the framework around it? That's the question. If you've made it this far, thank you. You're the kind of viewer who doesn't just watch rockets fly. You want to know why they fly, or don't. And if this video sparked your curiosity, consider checking out our next deep dive, where we explore the hidden risks of rapid iteration in aerospace, what it solves, and what it silently breaks. Because in the end, spaceflight isn't just about reaching orbit. It's about navigating everything between here and liftoff.